Okay, this is 3:32, so let's get started. And then it's my great pleasure to introduce Dr. Brian McDonald. He is currently an environmental engineer at NOAA, a chemical science laboratory in Boulder, Colorado. He has a lot of degrees under his belt, BA in economics and then BS in civil and environmental engineering at Virginia Tech, and then he came to California, Berkeley, got a master in science in civil and environmental engineering, PhD in civil and environmental engineering, but also master in public policy. And after that, he moved to Boulder. He became the CEROS postdoc, I believe, at CEROS and NOAA. And then while he was postdoc, he was awarded presidential early career award too. Then he is now at the environmental engineer at NOAA. So he's gonna talk about, introduce us about the new findings of the emission that traditionally we knew about, but also that we haven't really realized about the chemical products. So thank you very much, Brian, again. And then the floor is, actually the screen is yours.
All right, thank you. And thank you for the invitation today to present on our work in the NOAA Chemical Sciences Lab. And so today I'll be talking about work that we've been doing to help improve our understanding of anthropogenic emission sources over the US. So from, petroleum use both in the oil and gas fields where they're produced and also on the consumption side, which is used to power buildings and also as chemical products. And so just to get started with this talk, this is the trend in US energy production since the 1950s. And generally the trend for oil and natural gas production in the US has been increasing, especially in the last couple of decades. And this trend, at least earlier this year, was projected for oil to flatline by 2050 and maybe even grow a bit for natural gas by roughly 15%. And this increase in oil and natural gas has also coincided with a shift away from coal energy production and also a rise in renewables. And so if we look at where oil and gas is used and distributed in the US economy, so as I mentioned, most of it is used to power buildings and transportation. So the average person in the US uses about 4 kilograms of natural gas per day, 3 kilograms of gasoline, which mainly powers our passenger vehicle fleet, roughly 1.5 kilograms of diesel associated with our heavy duty freight sector. But there's also a fraction that's used for chemical products. So roughly 0.4 kilograms for plastic and rubber. And then this category we've called volatile chemical products. So these are everyday chemical products that whose emissions can volatilize to the atmosphere. And these are things like pesticides, coatings, inks, adhesives, personal care products, and cleaning. So mostly used for fossil fuel and energy consumption, but also a fraction for everyday chemical product use. And so some issues that are thinking about are this growth in natural gas is also proposed as a bridge fuel towards renewables. So it is true that if you switch from a coal to a natural gas power plant, generating plant, you generally have lower emission intensities of carbon dioxide, and then also nitrogen oxides and sulfur dioxide. So this is a nice paper summarizing this by GEOSTATIONARY in 2014. That's what's shown on the left. But there's been a lot of recent research trying to understand fugitive sources of methane that can also be emitted in these oil and gas fields. And there's a paper in Science a few years ago showing that these methane leaks are potentially underestimated by roughly 40%. And the 20-year rate of forcing of these methane leaks are comparable to the CO2 that is combusted from that natural gas that's extracted. And then on the consumption side, as I mentioned, oil is largely used in our transportation sector, mobile source engines. This includes both on-road transportation as well as engines that may be on off-road, including diesel locomotives, construction equipment, ships. And mobile sources are still an important source of greenhouse gases and air pollutants to the atmosphere. So roughly 30% of CO2, 40% of carbon monoxide, half of NOx, and a fraction, roughly 50% of anthropogenic VOCs. And these emissions contribute to both summertime ozone and winter haze events. And so in 2018, we dug in more deeply into non-methane VOC emissions associated with the petrochemical industry. So the left column shows, again, that sort of what I showed a couple slides ago, but just how much natural gas, gasoline, diesel is produced in the US. And then tracing it through various aspects of the chemical industry to the last column, where we estimate the non-methane VOC emissions to the atmosphere across this life cycle. And what we found is maybe roughly a third of those VOC emissions are associated with oil and gas production and refineries or other chemical facilities. There's still a fraction that come from mobile source engines. And then what we found was that actually one of the largest sources and fractions was coming from these volatile chemical products, or roughly half of that total. And these are expected to be in population centers and an important urban source. And so one of the reasons why we're interested in understanding these emission sources, including across the petrochemical industry, are that these are important precursors to ozone and aerosol formation. This is a nice plot showing mortality from all weather phenomena. So NOAA, in partnership with EPA, is responsible for the operational air quality forecast for the US. And that forecast also helps generate those, or in partnership with regions and states, generating smog alerts. And if you look at the mortality across all weather, air quality is by far the largest impact on human mortality. So on the left, you see some extreme weather, including lightning, tornado, hurricanes, heat. You add that all up, air pollution still is larger than all of that. And it's even more pronounced when you plot it on a linear scale, which is shown on the right. So air pollution is an important aspect of the weather forecast modeling system, and also has impacts on society. And then just in this context of air quality forecasting, one of the challenges has been, well, we're now in the second year of this COVID-19 pandemic. We know that there have been major changes in people's behaviors, emissions activities, and yet the emission inventories we generally use are often, they take a long time to develop. They usually have a 3 to 4 year time lag. And so, how do we start using some of the Earth monitoring capabilities that have been launched into space, as well as the extensive ground monitoring network, so that we can update emission inventories more quickly, so that we can account for major events like the COVID-19 pandemic now. But in the past, the 2008 Great Recession also was another a time period where there were big changes in emissions that also affected air quality forecast models. And this is not just an issue for NOAA, but this has also been an issue for other air quality forecasting agencies in other parts of the world, including the European CAMS service. So with that sort of as a background for this talk, I want to get into the first emission sector that I'll be showing some of the work we've been doing on better quantifying these upstream oil and gas emissions. So we have several objectives here. One is to understand ozone and aerosol precursors, so mapping out the emissions of NOx and volatile organic compounds, as well as the methane that's emitted along with NOx and VOCs. Do some evaluations with recent advances in satellites that are being launched into space, including TROPOMI, and then also get a sense of how these emissions might have been impacted during COVID-19. And so this was work started by a graduate student of mine, Alan Gorchak-Negron, who's now at University of Michigan with Eric Hort. But he looked at ways of quantifying oil and gas emissions, starting with the combustion. So in these oil and gas fields, you have a lot of engines. So, you know, associated with exploration, drilling, hydraulic fracturing. You have dehydrators, heaters, compressors, things that are transmitting the oil and natural gas through pipelines and to processing facilities. So there's actually quite a bit of energy that's used to just extract the energy out of the ground. And so what Alan did was also connect this to nitrogen oxide emissions, because NOx is something that is easier to detect from space and highly related to, you have the NOx because of the combustion that's occurring. And so this potentially gives us a way of tracking changes in oil and gas production just by looking at NOx. And so following that work by Alan Gorchak-Negron, Colby Francoeur, who's a graduate student with me right now, expanded this work to map the emissions over the entire continental US. Our focus has been on the onshore oil and gas production, which is roughly 80% of the US total. The boxes show where, so in 2013 and 2015, NOAA deployed its P3 aircraft and flew over many of these basins from Texas all the way up to the Bakken and including to the Marcellus in Pennsylvania. And so we are able to use these aircraft measurements to derive aircraft fluxes from these measurements and compare it with the inventory. And so I'll refer you to this paper that was published earlier this year by Colby, but in general, these maps of emissions of oil and gas NOx emissions agree fairly well with the aircraft derived fluxes. So one of the interesting phenomena we noticed when we looked at the aircraft data is in that top right panel. And what we noticed is that the methane enhancements correlated quite, tended to have a consistent correlation with the nitrogen oxide emissions. And so what this plot here is showing is the dark blue bars show we've taken that bottom up and then nitrogen oxides emission maps and apply it with this tracer correlation from the aircraft to estimate methane emissions. And that's what's being showed for various basins in the dark blue. And we also calculated it more in a traditional, using these mass balance techniques where you fly the aircraft on the upwind, downwind legs and back out what the emissions are. And that's shown in the light blue and fairly consistent estimates of methane using these both approaches. So what the bottom line here is that we think that by first estimated NOx emissions, that also gives us some insights on being able to infer these fugitive leaking sources of methane as well. And it's not that the methane is coming from that, these fugitive methane sources aren't necessarily coming from the same engines that are producing the NOx, but they are co-located. These fugitive methane emissions are co-located where you have, these processing and drilling activities that are emitting NOx. So in addition to methane, working with my colleague Jessica Gilman, who had canister sampling on the aircraft, looked at the NMVOC to methane ratios and noticed that depending on the basin, you could have more NMVOCs relative to methane in basins that are wetter or have a larger fraction or have more oil production relative to natural gas. And in the drier basins, you tended to have less NMVOCs relative to methane. And also with these measurements, Jessica was able to determine also differences in the composition of the VOCs that are emitted in these basins. So the wetter basins tend to have more aromatics, whereas the drier basins tend to be more of the light alkanes. And so putting this all together, Colby revised sort of the budget of oil and gas emissions. So just sorting for NOx, not a lot of changes here, and then also oil and gas production is not a major source of NOx in a continental US perspective, but as I'll show on the next slide, it can be a regionally important source of NOx. But where the biggest changes occurred, kind of consistent with that Alvarez study earlier published in Science, is that yes, it looks like these methane emissions are being underestimated by factor 2, so that's going to affect, also have some implications on radiative forcing on climate. And then what was probably new in this study was, in addition to methane, methane is not coming out by itself. It's also coming out with all these other non-methane VOCs that can impact air quality. And similarly, these emissions are probably underestimated by a factor of 2 as well. And so one thing we've done since this work is really try to better connect this to the satellites. And so this is work by Barbara Dix, a colleague at CU Boulder, looking at the Tropomi satellite. So Tropomi gets pixels of roughly 3 by 7 kilometers, so a higher resolution than the previous satellites, which were more like 13 by 24 kilometers. And what Barbara's really been looking at, historically when we've looked at these NO2 maps, we generally our eyes get drawn to the cities and to large industrial facilities. But what Barbara has done is try to look at other sources that we might start being able to see, especially with these higher resolution satellites, including over oil and gas areas. And so, some of these oil and gas areas like the Permian, which is located in Western Texas and the border of New Mexico, actually have quite significant NO2 enhancements that can be comparable to a medium-sized US city. And in several of these other basins, you also see noticeable enhancements of NO2 above the regional background. So I'm going to focus on the Permian because the Permian is a major oil and gas producing region that accounts for maybe 1/5 of US oil and natural gas production. And so what we've done is using the emissions inventory that Colby has developed, this fuel-based oil and gas or FOG inventory, and started evaluating in a chemical transport model called WRF-Chem and comparing it with Tropomi. So the Tropomi retrieval for the Permian in West Texas is shown on the right for nitrogen dioxide. And on the left is the WRF-Chem simulation without oil and gas emissions, and the 2 circles just denote there are 2 cities there, Midland and Odessa. And so it's clear that the NOx in this region cannot be accounted for by these 2 cities And when we include the oil and gas emissions, then we start being able to see what the satellite sees, both in the absolute magnitude of the NO2 column, but also in the spatial pattern. So tropomi measures not only nitrogen dioxide, which is helpful for understanding NOx emissions, but also measures formaldehyde. And while there are some direct emissions of formaldehyde, a lot of the formaldehyde in these oil and gas basins are actually generated through secondary processes. And so here again, showing the tropomi retrieval on the right, the WRF-Chem modeling with no oil and gas emissions to the left, and in the middle is when we put in the oil and gas emissions of NOx and VOCs, then again, pretty promising sort of reproducing the magnitude and spatial distribution of that formaldehyde that the satellite is seeing. One other thing we were curious about is sort of the role of NOx and VOC. So in the bottom left, we added only oil and gas VOCs to the no oil and gas case, and on the right, we added just NOx emissions for oil and gas. And the point here is that this is, this chemistry is coupled, right? So if you have more NOx emissions, it also leads to enhanced formaldehyde production. And so it's important to consider both the NOx and VOC when we're looking at the satellite retrieval of formaldehyde. So as I mentioned, one thing we've been looking at more recently is using these, our approaches for estimating oil and gas emissions, which we now think we can do on a monthly basis, on a fairly near real-time basis. And so one of the things that happened during the pandemic is that a lot of the drilling activity fell off, but the actual production of oil and natural gas was more or less, there was some reduction, but more or less steady during this period. So it's just the new exploration that was really impacted. And so NOx can be affected by both the drilling and the production, but there have been some studies looking at the VOCs emitted from oil and gas, and they tend to be dominated by the production phase. So maybe there's some reduction in oil and gas VOCs due to the pandemic on roughly a 10% type of scale. And so this is work by a colleague of mine, Jen Hay, looking at, so tropomi can also measure, has retrievals of methane. And what she did here was look at how methane changed in 2020 versus 2019. And what the satellite sees is generally increasing methane concentrations. And interestingly enough, that the WRF-Chem model captures some of these increases in the methane concentrations. So we're still trying to dig into this a little bit more. It is maybe a little counterintuitive to us. We thought that maybe with the impacts in the oil and gas sector, you might expect methane to go down, but maybe there are other emission sources of methane that are not associated with oil and gas, like wetlands or agriculture, that were impacted in different ways, or also whether there's influence of chemistry and OH budgets on the methane lifetime. So we're still trying to figure this out, why the methane is going up, but something we got to dig in further. So overall, we've estimated, there seems to be higher methane NMVOC emissions by a factor of 2 than what's in our current regulatory inventories. I think the satellites provide a promising constraint on nitrogen dioxide and formaldehyde. And I think we're trying to also see what the or how these satellites can be used to constrain the greenhouse gases, although there are some non-obvious trends that are going on. So that was mostly on the supply side of things, but now I want to shift the rest of the talk to the demand side. And so here I'm going to focus more on the air quality aspects. And so early on in the pandemic, there were a plethora of studies that came out on COVID-19 and air quality. And this is a review paper that our lab was part of with Ulick, looking at some of the early findings from these studies. And what my colleague Georgos Gatzelis found was it's important to to control for the effects of meteorology to be able to relate it to the emissions. And so what this plot is showing here on the x-axis is there were these stringency indices that kind of evaluated how stringent COVID-19 lockdowns were across different regions of the world. And as these lockdown measures became more stringent, you tended to see decreases in the NO2 concentration, which corresponded to decreases in PM 2.5 and maybe slight increases in ozone. But one of the limitations I'll point out is that a lot of these early studies looking at COVID-19 and air quality tended to focus on periods where, at least with respect to ozone, in the winter and spring, which are not necessarily the peak ozone season, and then also looking at more average ozone values versus high ozone values, which are really what are guide some of the national ambient air quality standards. So our laboratory in 2020 pulled some instrumentation together to be able to make measurements during the COVID-19 lockdown period. Some of the key questions are listed here. So how have reactive nitrogen emissions and chemistry changed in urban areas? How have the organic emissions and chemistry changed, especially of these volatile chemical products? And then the last part is showing some preliminary modeling results on how it may have impacted tropospheric ozone. So earlier this year, my student Colin Harkins published a paper in ERL using kind of similar fuel-based approaches we've used to estimate the oil and gas combustion, but now for the motor vehicle sector. So turns out Department of Energy do report monthly fuel sales data that we can get down to different regions, state level in some instances. And then once we do that, we can estimate all the co-emitted air pollutants that are associated with that combustion. So just here showing the CO2 changes, so somewhere between 30 to 40% changes in April 2020 relative to the previous year. Another advantage of looking at the fuel sales is that we can separate the gasoline from the diesel. So the gasoline is mainly consumed in the passenger vehicle fleet and the diesel in heavy duty. And so what Colin and others have noticed is big drop-offs in the light duty traffic in April 2020, kind of rebounding, but still somewhat lower than normal by July. And then on the heavy duty side, maybe not as much of a impact, maybe a roughly 10% decrease, but not as much as on the light duty side. So one thing we've done is, we can estimate these emission maps for each month during the pandemic, and we started comparing this with what the Tropomi satellite was doing with my colleague Shova Kontragunta at NOAA. And so on the left is showing what Tropomi sees. She's, without getting into too much detail, she's applied some techniques to reduce the influence of meteorology when looking at different years, but overall generally decreasing trend in NO2. And then on the right, what she's done is looked at the Tropomi changes in 2020 relative to 2019 for each month, and that's shown in orange, and it's roughly tracking the expected changes in NOx from the changes in fuel use for light and heavy duty engines. Since that study, we've also started trying to update emissions for other sectors, including industry. using, turns out there's a lot of information on the US energy sector and economy on monthly timescales that now we're starting to try and use to be able to update these emission inventories in a more near real-time way. And so just in general, April, bigger reductions, kind of broad-based reductions in NOx across different sectors, maybe roughly 20% in total, and maybe getting halfway back by July, 10% reduction or so. So with these updated sector-based emission adjustments, we wanted to put this into the WRF-Chem model and evaluate it with, so we do 12-kilometer continental scale modeling, simulate this with full gas aerosol chemistry. And our focus has been on trying to better understand how these impacts affect the ozone season between 2019 and 2020. And so our analysis largely focused on the satellite data sets, as well as flights that were made by University of Maryland over New York City during the COVID-19 lockdown period. And so here is some model evaluations by Jen Hay. So the business as usual emissions are shown with the blue dots. The COVID adjusted emissions are shown with the pink dots, and the gray dots show the aircraft observations. And so over this April to July period of 2020 of these flights over New York City, it's clear that, the business as usual emissions, as we would expect, would overpredict the NOx concentrations due to the pandemic that was impacting the city, and that lowering these emissions does improve the model observation agreement. Just pointing out the importance of why being able to update emissions more quickly for our air quality forecast models has kind of risen as a need within NOAA. Again, so that was looking at aircraft data, but we've tried to look at it more with tropomi nitrogen dioxide data. And so what tropomi sees between 2020 and 2019 is shown in the top for April and July, and the bottom is WRF-Chem. And the boxes kind of show high emission source regions, so either large cities or large point sources. And in these places, the WRF-Chem modeling and the satellite tend to agree better. But if you notice in the top row, there's a bunch of red pixels in the satellite, suggesting maybe there might be increasing NO2, and we're not quite sure if that's real or sort of some satellite uncertainty. But at least over these high emission source regions, it seems like there's general consistency in what we might expect from how COVID would affect NOx emissions and tropospheric NO2 changes. And then this is kind of follow-up work. Now we're in the second year of this pandemic. And so there's a lot of questions about, well, how is, there were questions about how air quality changed due to lower emissions, but now we're sort of in the second year where things may have gone back up. And so has air quality moved in the other direction? So, or nitrogen dioxide. And so one of the, so a lot of work has focused on the tropomi satellite because it's got the highest resolution that you can see around the world. But in 2021, there was an algorithm change, so there's not a consistent data set to look at the moment, pre-COVID, during COVID, and in this recovery period. But what have done here is work with colleagues at University of Maryland, looking at another satellite called OMPS, which also measures tropospheric NO2 on the NOAA 20 satellite. This was launched in 2018 and has a consistent record of how tropospheric NO2 has changed before, during, and after. So this is what OMPS sees, kind of a lot of what also Tropomi saw, generally reductions in 2020 versus 2019 in this COVID lockdown period. And this is showing sort of the rebounding. So between 2021 and 2020 is that there has been generally an increasing trend over many of these areas of the US where there were reductions previously. And so the last thing is we've looked a little bit more closely at the traffic data we've used for updating the mobile source inventory. And this is just an example for Los Angeles. So the gray shows kind of what the emissions or what the traffic levels were before the pandemic. The black is the actual consumption during the pandemic through 2021. And again, noticing that things kind of rebounded by July of 2020, but have still somewhat stayed a little bit lower than normal even through this year. So just to summarize, I think one of the things we've learned is that there's actually a lot of publicly available data on energy and the economy that we can use to update emission inventories more quickly from a bottom-up perspective. We've tried to do some model evaluation with satellites as well as aircraft data to see how well these more near real-time updates are captured, at least over the largest US cities. And as we're getting through the second year, while things have rebounded and recovered from the pre-pandemic levels, there still seems to be some fraction of traffic that is still not what was there before the pandemic. So this could still be associated with, people. There are some people like myself who are still working remotely and not commuting every day back and forth. So the last thing I just want to talk about is how have the urban VOC emissions changed? And so, a lot of people familiar with the lower traffic on our roads, but this was an article on CNN suggesting that ice cream sales are up with more people at home, but deodorant sales are down. And so what I want to investigate in the next part of this talk is, can we use our atmospheric observations to see whether these economic trends are detected? And so just to give some background here, so in the past, right, it was pretty clear that a lot of the anthropogenic VOCs were coming from motor vehicular sources. But with the advent of catalytic converters over the last 5-6 decades, there's been a dramatic decrease in the tailpipe emissions of VOCs, such that today, roughly half of that anthropogenic VOC budget in LA is potentially from these volatile chemical product emissions. Since the LA study, we've made measurements in New York City and also done modeling in New York City. So this is an example of a high ozone event that occurred during a heat wave. And this is a study published by my colleague Matt Coggin this year, showing that anthropogenic VOC emissions do contribute to this high ozone here. The rough split is maybe half of that anthropogenic VOC contribution to ozone from the mobile source emissions and half from the volatile chemical products. So in 2018, we made these measurements using proton transfer reaction time of flight mass spectrometry, as well as gas chromatography mass spectrometry in Boulder, Colorado, and New York City in 2018. And we've done source apportionment of these VOC measurements between these two cities. We also made a bunch of mobile laboratory measurements across 5 different cities in the US between New York City and Boulder, Colorado, where we were able to identify tracers to be able to do source apportionment. So D5-siloxane is a compound mainly found in personal care products, and parachlorobenzotrifluoride is a compound mainly found in coating-related emissions. And then just showing on the right that these measurements have been made by our group in Boulder between 2018 and 2020. And actually in New York City, the groups, John Mack and Drew Gentner at Yale and Stony Brook University also have made similar type of measurements during the COVID lockdown period in New York in 2020. And so what I'm showing here is just the time series of these various tracers. So D5 siloxane, again, for personal care products, this parachlorobenzyl trifluoride shown in brown. There was a period where there was actually construction at the laboratory, so we weren't able to use the data in May for this, at least these construction tracers. Ethanol, while it's in gasoline, our prior PMF analysis has shown that it seems to be predominantly from personal care and cleaning products. And then in the bottom is benzene, which is from mobile sources. So you're not allowed to put benzene, it's a carcinogen, in chemical products. And so what we've done here is look at, if we can estimate the benzene emissions from all the mobile source emissions work that we've done due to the COVID-19 pandemic, we're looking at enhancement ratios of these tracers relative to benzene to be able to infer how these volatile chemical product sectors may have changed due to the pandemic. And so that's what's being shown here. So the black shows our estimate of how mobile source emissions or benzene changed during the pandemic. So, 50% drop in this April-May time period of 2020. And the atmospheric observations is pretty much the D5 to benzene ratio didn't change very much, whether it was before or during or in this recovery period of the pandemic, and hence why the personal care product tracer follows the mobile source trend. One other thing we did was look at, turns out there are information on retail sales of personal care products that are tracked by Department of Commerce. And looking at these retail sales, it does corroborate that there was drop off in the personal care sector comparable to the changes in mobile sources. So again, this PCBTF compound is our tracer that we look at coatings, and in contrast to the D5, the measurements are suggesting that PCBTF tended to increase throughout this period. And again, if we look at these retail sales, there's retail sales of building material like the Home Depots or Lowe's of the world, and they tend to show increasing trends over this time period. So as people were at home, they may have been also doing more home improvement projects, as well as construction activities seem to still go on. We looked at other tracers. So again, ethanol is used in personal care and cleaning products. That tends to follow more this D5 siloxane trend. And then we've also looked at D4 siloxane, which is a tracer we've identified for adhesives. And so it tends to follow more of this building materials, this PCBTF type of trend. So the bottom line is, VCP emissions are also affected by changes in that occurred due to the pandemic, but maybe potentially in offsetting ways. So the last thing I'm just going to cover here is just translating this to modeling of ozone in 3D chemical transport modeling. So before I show the changes in NOx, and all I've done is added what are expected estimates of how anthropogenic VOC emissions might have changed in 2020 versus 2019. And the bottom line is that, again, these changes are similar to NOx, are probably somewhat broad-based across many different sectors of the US economy, not just the transportation sector. And these anthropogenic VOC changes are roughly similar to the changes in the nitrogen oxide changes as well. And so what Jen has done here is, and then I'll just focus on the July period, because there's still COVID-19 impacts and it's in the middle of the ozone season. So what Jen has done here is looked at the number of ozone exceedance days. So this is for July of 2019, and that's shown from the AirNow monitoring network across the US in the bottom. So roughly 990 days of ozone exceedance events. The top shows the modeling and WRF-Chem if we use our business as usual or 2019 emissions. And so generally the model is capturing the number of exceedances as well as the general pattern, although there seems to be something going on in the Central Valley of California that our model is not able to estimate, potentially related to uncertainties in agricultural emissions. So what Jen has also done is model the same time period in 2020. And so in the observational network, the number of ozone exceedances goes down slightly in 2020 versus 2019, maybe by 15%. But if we model the business as usual emissions or the 2019 emissions in 2020, there's actually quite a big increase owing to just differences in meteorology between 2020 and versus 2019. So roughly we attribute roughly 70% increase that would have been there if there wasn't the pandemic, simply due to meteorology. And then when we cut the emissions, both the NOx and the VOC emissions, we get roughly a 40% reduction due to changes in NOx and VOCs, which brings it in better agreement with the OBS. But I just want to make a point here, which is a lot of the studies have looked at, have focused on NOx, partially because that's things that we can see fairly easily from the satellites, from nitrogen dioxide. But I just want to raise the point that it's also important that we consider the changes in anthropogenic VOC emissions, and that they can influence the ozone exceedances, not just in the western semi-arid US, but can also matter, especially on these type of heat wave events that are conducive to high ozone over the East Coast, as we've shown previously over the New York City region. So just to summarize, we do see changes in some of these VCP tracer compounds, although it varies kind of by some of the subsectors. And our preliminary modeling suggests that overall the impacts of the COVID-19 pandemic on anthropogenic emission sources would suggest that they do tend to lower the number of high ozone or exceedance days. And so I just want to acknowledge the team of modelers that I've been fortunate to work with at the NOAA Chemical Sciences Lab, mostly presenting their work here, as well as the close collaboration with our experimental groups in the tropospheric chemistry measurements group, and then also all the external collaborators as well as funding sources. And that's really what I have to present here. I do have a couple more slides to just show kind of the future efforts that NOAA is planning right now. And so in 2023, we're planning a heavy research aircraft campaign called AROMA. So it stands for Atmospheric Emissions and Reactions Observed from Megacities to Marine Areas. The goal, there's two parts to this aircraft campaign. One is to look at further study the emissions and urban air quality questions, especially related to these volatile chemical products and anthropogenic VOC sources. It's because it's now being planned for 2023. It will also coincide with the TEMPO geostationary satellite. And so we'll also be looking at new satellites as well during this period. And the other component is looking at recent advances by Patrick Veras in the NOAA Chemical Sciences Lab over the remote marine atmosphere and at new insights into the sulfur cycle. And right now, this is being planned to take place on the NASA DC-8 aircraft between May and August of 2023. It has two deployments, one to the West Coast. So this part of the deployment will be more focused on the marine Pacific atmosphere, although we do have flights planned over the LA basin. And then it'll shift over to the East Coast, where the focus will be mainly on looking at other US cities. There are other aircraft assets that are being deployed. So NSF is deploying the C-130, the Gotham field campaign, led by John Mack and Stony Brook. So there'll likely be some coordination with that campaign over the East Coast, as well as a NOAA Twin Otter that will have remote sensing of also atmospheric dynamic capabilities, as well as coordination with the NASA G5 aircraft, which will have a atmospheric composition remote sensing package that will coordinate with the DC-8. So a lot of field efforts are being planned in 2023 that coincide with even newer generations of geostationary satellites, and hopefully will help us better understand emissions and chemistry. So with that, I'd like to thank you for your attention.
Thank you very much, Brian. And then if you have any questions in the audience, you can either type or raise your hands, maybe. And I can, maybe you can unmute yourself, I guess, even. Any questions? So let me start about the questions. For the COVID pandemic, it seems like you saw the decrease of NOx, but in Southern California, it seems like the day after, a couple of weeks, at least in April, there were no cars on the interstate. So I think I could even cross over the 405 just by walking. There's not much cars. So I expected more than 20% of NOx emission. It seems like our base emission is very high. Then it's going to be extremely difficult to cut off for NOx, much of it, you think? Or...
Well, I think part of that is because a lot of NOx is also coming from the heavy duty sector, right? And so it also depends on freight, right? And it seemed like that was still going on, right? People were still
buying stuff,
ordering goods, right? And if anything, right now we're potentially facing, the increased demand for online goods, right, is stressing the supply chain infrastructure.
Right. So the future of the electric cars advent may not be that helpful in terms of NOx reduction. That's what I can see there. I think Gurat raise your hands, so you can unmute yourself and then ask questions.
Oh, hi, Brian. Thanks for the nice talk. I just wanted to ask a question about. I know this is all focused on the U.S. and your perspective is primarily pollution. In terms of, what are the lessons to be drawn in a global sense, especially with respect to methane emissions? And that's one area I feel like that could be some, in terms of, estimates of methane from fossil fuel sources globally that's attributed to oil and gas industries.
Yeah, I mean, that's one of the questions we were trying to see if we can, tease out in these Earth observing systems, the satellites, right? Our expectation was there was a big drop off, right, in oil consumption, right, just from gasoline and cars not driving on the road, and seeing, and so our expectation was maybe the methane emissions from oil and gas probably would have some reduction. And right now it's kind of, I think, the increase in methane just more generally over the past decade or two is a bit surprising or accelerating. And I guess I wonder, one of the things I do wonder about is also the interaction between also the atmospheric chemistry or changes in OH concentrations on methane, right? And if you're having reductions in a lot of these air pollutant emission sources, does that also have implications on the methane lifetime that we also need to consider? And you're probably going to see more of that impact on a global scale than, say, if you were just focused on a single continent. And I know, people who are looking at methane in the global models like GeoSchem are, they are raising the importance of understanding trends in OH and understanding how methane has trended and how methane and then that inference on methane emissions.
Thank you.
Any further questions? So I can see your window is dark already out there in Boulder, Colorado. So probably you should go out and then have a dinner. So let's thank speaker again. Thank you very much, Brian, to give us a seminar. Thank you.
All right, thank you.